Hi, my name is Hojin Park from Carnegie Mellon University, and today I'm going to talk about the Burstable storage service on public clouds, in which how to exploit the service for high-performance storage, and some use cases of this service using our approach. This is a joint work with my two advisors, Gregory and George Amvrosiadis. In general, the price and performance of storage services of public clouds are guaranteed by SLAs of public cloud providers. For example, on AWS, the performance of general-purpose SSD is guaranteed as 3 IOPS per provisioned volume capacity gigabyte. So, if you use 100 GB of that type of storage, 300 IOPS is guaranteed as a baseline throughput by the cloud provider. Recently, some public clouds, such as AWS and Microsoft Azure, started to provide the service called Burstable Storage Service, in which every burstable storage initially has credits called burst credits, and when your volume requires more than the baseline performance, it uses the burst credits to burst to the level of required performance. So, in the same example, this SSD can burst up to 3000 IOPS if it needs higher performance than the baseline throughput by using the burst credits it has. Burstable storage service allows users to deal with the bursty workload characteristics that many workloads experience occasionally. Let me show you how a burstable storage service works by using concrete example in AWS. Assume that we are using 100 GB of general-purpose SSD, and these two graphs show the status of the volume in terms of storage performance and the amount of burst credits left. The x-axis of the upper graph is time, and the y-axis is storage performance in IOPS. The x-axis of the lower graph is also time, and the y-axis shows how much burst credits left in the same volume. When you use 100 GB of general-purpose SSD, its baseline performance is guaranteed as 300 IOPS, and it initially has 5.4 million burst credits. So, when this storage volume is less than or equal to the baseline performance, no burst credits are used, and the volume can serve the performance it requires to serve. When the volume needs to serve higher performance than the baseline throughput, it can burst to that level of performance by using burst credits until some burst credits are left. In this case, the volume is bursting at the level of 3000 IOPS by using 2700 IO credits per second, which allows it to burst for 33 minutes. And finally, when there is no burst credits left, the volume cannot burst over the baseline performance, but can still serve up to the baseline performance. When the volume uses less storage bandwidth than the baseline performance, it gradually accrues the burst credits. Now, I'll explain two interesting aspects of burstable storage service and how did we exploit these two properties to achieve high performance for extended duration. The first property is that every new burstable volume starts with a certain amount of burst credits. So, as you can see in this figure, if there is a volume that used up all the burst credits, we can replace that old volume with the new volume that has full burst credits. Note that some applications that does not need to keep data persistently can simply remove the old volumes and replace them with the new volumes. However, some applications need to make sure that the data in the old volumes are safely migrated into the new volumes before they are deleted. I'll explain more about it in the later slides. The next interesting property is that the burst credits are assigned per volume, and every burstable volume can burst up to the same level of performance regardless of the volume capacity. In contrast, price and baseline performance are proportional to the provisioned volume capacity gigabyte. Therefore, by splitting a volume into multiple smaller volumes, we can achieve high performance without paying additional cost. This example again shows the case study of general-purpose SSD on AWS. If you use 500 GB of SSD, the baseline performance is 1500 IOPS. And by using the storage bursting feature, it can burst up to 3000 IOPS by using burst credits. However, If you use 10 50GB SSD instead of a single 500GB of SSD, each small SSD can burst up to 3000 IOPS, so the aggregated burst throughput of that set of 10 small SSDs is 30,000 IOPS, which is 20 times higher than the baseline throughput of the 500GB SSD, and even 10 times higher than the burst throughput of that single SSD. Note that these three cases charge the same price because the price is calculated per provisioned volume capacity. To wrap up, by exploiting these two features of Burstable Storage Service, we can achieve high performance for extended duration. Now let me introduce three use cases that can take advantage of using Burstable Storage Service. Our first use case is persistent data storage, which is the most basic storage type that stores data until it is deleted. Since the persistent data storage should keep the data persistently, when the old volumes are replaced by the new volumes that have full burst credits, the data must be migrated from the old ones to the new ones safely. Although this data migration causes some amount of overhead, and it makes this first use case the least well-fit of the three use cases, this is still huge performance gain, even with naive implementation of the design. Our second use case is SSD caching with write-through policy. In a single machine, people often use SSD as a caching layer on top of the HDD because HDD is cheap but slow and SSD is more expensive but faster, so that it can save large amount of data in the underlying HDD while taking advantage of high performance SSD for cache data. In this case, no data migration is necessary when replacing the old burstable volumes with the new ones. So we can simply delete the old ones and attach the new volumes to be used as an SSD cache. This property makes SSD caching to be better fit than the persistent data storage. However, after the volumes are replaced, there is no cache data in the new volumes, so that we should wait until the SSD caching layer is repopulated to achieve the high performance again. Our last use case is ephemeral data storage, which is very common storage type in scientific applications or cloud programming frameworks to save intermediate data in their data pipelines or to save checkpoint data. It is perfectly suited for using burstable storage because the short-lived nature of ephemeral data works well along with the burstable storage service. In this talk, I'll further explain our prototype design and evaluation of the first use case, persistent data storage. As I mentioned earlier, it is the toughest use case to use our approach because of the data migration process, and the ephemeral data storage is expected to achieve high throughput without any penalty. So please check out our paper to see more details and evaluations of the other two use cases. The design of persistent data storage exploiting burstable storage service starts with using n small burstable volumes in a RAID 0 array as a data storage. As we mentioned earlier, our prototype uses multiple small volumes instead of a large capacity of a single volume to exploit high aggregated burst throughput of multiple small volumes. And we used software RAID for the ease of implementation, but any other tools that can aggregate multiple volumes can be used instead of RAID. After some amount of time of using this persistent data storage, burst credits will be used up and the credits will run low. This orange color represents the quantity of burst credits remaining on the volume. So the partially full canisters indicate that those volumes have only a fraction of their original burst credits remaining. Then we create new set of small burstable volumes that initially have full burst credits. To migrate data from the old volumes to the new volumes for data persistence, we used RAID1 rebuild process between each pair of volumes. Again, we used software RAID for the ease of implementation and because it also allows data to be available even during the data migration process. But any other tools that are similar can be used instead of software RAID. And finally, after the data is safely migrated into the new volumes can be used as persistent data storage for a while until the burst credits run low again. This cycle allows users to exploit high-performance persistent data storage continuously. We evaluated our prototype of persistent data storage to answer the following two questions. How much performance gain we obtain by exploiting Burstable storage service? And how much overhead is incurred by data migration process in our design RAID 1 rebuild process? As an evaluation setup, we experimented on AWS and attached general-purpose SSD storage volumes to C5 9x large instance to evaluate the performance of our prototype. As a baseline, we used 100 GB of a single SSD volume and measured baseline performance of the volume. And as the prototype of our design, we used 10 GB of general-purpose SSD and measured aggregated burst throughput of the volumes and replaced the old burstable volumes every 22 minutes with the new volumes with full burst credits. Lastly, we measured storage performance using Flexible I/O Tester FIO tool. This graph shows the performance comparison between the baseline and our design. The x-axis is time, and the y-axis is storage throughput in IOPS. The higher, the better performance. This green line shows the baseline in which 100 GB of general-purpose SSD performs at 300 IOPS as a baseline throughput, regardless of read-write ratio of the workload. The blue line shows the performance measurement of our design for read-only workload. As you can see here, during the non-rebuild time, our design achieves 30,000 IOPS, 100 times higher performance than the performance of the baseline. Although there are throughput dips every 22 minutes during the data migration process, which is RAID 1 rebuild process in our design achieves really high performance gain during the non-rebuild time. For read-write equally mixed workload, our design shows the same performance gain during the non-rebuild time, but worse throughput dips during the rebuild time. We suspect that during the software RAID 1 rebuild time, both read and write are available, but the write performance is affected more by the data migration process. But our design still achieves high performance gain during the non-rebuild time for read-write mixed workload as well. This evaluation result gives some implications. For only 10% additional cost incurred by the data migration, our design achieves 100 times higher throughput than the baseline, and even when accounting for rebuild overhead, it achieves 93 to 99 times higher performance in average. Also, we empirically checked that the rebuild time is proportional to the volume capacity of the small burstable volume, so that by using more number of smaller capacity volumes, the rebuild time can be reduced. Another way of mitigating the throughput dips during the rebuild time is replacing a single volume at a time, instead of replacing all the volumes at once, so that the performance degradation can be spread out for the longer period. In conclusion, there are two properties of burstable storage service in which every new burstable volume starts with a certain amount of I/O credits, and the credits are assigned per volume. By using these two features, our design achieves up to 100 times higher performance at only 10% higher price. Our way of exploiting burstable storage service also gives some implications to both public cloud providers and cloud users regarding the way of using service provided by public clouds and some science behind designing SLAs of public clouds. Lastly, please see our paper for more details on the other two use cases and more evaluation results. So in this workshop, we want to open some interesting discussion topics. First, are there any other suitable application types that can benefit from burstable storage service? And how should cloud storage pricing and SLAs should be designed to address these unintentional opportunities? For example, those aspects of burstable storage service can be further improved, like burstable instances or spot instances to let clients to actively exploit it, or it can be changed into the way of preventing clients from exploiting these features. Thank you for your time, and I'll be happy to answer your question.